Hey guys, before you start your work today, I wanted to give you an overview of what we have learned or what we should have learned so far. So the first thing I wanted to talk about is what we learned about basically what we reviewed about graphing rational functions in lesson 421. So in lesson 421, we talked about how to graph something in the form y equals a over x minus h plus k. So when we're graphing that, the first thing we want to notice is the horizontal and vertical asymptotes. So the vertical asymptote is going to be where the denominator is 0. So in this case, if you have x minus h, that's going to mean that that is where the vertical asymptote is located at h. So if you had x minus 2, that would mean that the vertical asymptote would happen at 2. The other piece was the horizontal asymptote happening at k. So for example, if you had 1 over x plus 3, then that would mean that the horizontal asymptote happens at y equals 3. And then we also have a, which is like the stretch factor. We didn't talk as much about that, but if you recall, that's going to go ahead and tell you for the a value, it'll tell you when you move over to the right by 1 from your locator point, that's going to be where the asymptotes intersect. It'll tell you how much you go up or down. The second thing that we talked about was if you are given a rational function that's not in its graphing form, for example, the quantity 3x plus 5 divided by the quantity x plus 2, that's going to be easier to deal with. We're going to be able to identify the horizontal and vertical asymptotes and the stretch factor. If we do one of two things with it, we can divide it. We can also use the kind of cool fraction decomposition method that we explored in the last class. So the first way is just by dividing. So if you divide 3x plus 5 by x plus 2, x plus 2 goes into 3x plus 5 3 times. But that leaves you with 3x plus 6, which means that you're going to end up with a remainder of -1. And so that means that all in all, your new rewritten expression would be y equals 3 plus, and then you have your remainder of -1 divided by the original denominator of x plus 2. So once it's in this form, you more clearly see where the horizontal asymptote will be at 3 and how the vertical asymptote will be at -2. The other way that we talked about being able to rewrite it into this form was by breaking it up into like a giant 1. So for example, you may see that x plus 2 goes into 3x plus 5 3 times. 3 times x plus 2 divided by x plus 2. But 3 times 2 is 6, so we need to subtract 1 more. So subtracting 1 over x plus 2, and that's going to lead us into the same path. It's just a different way of thinking about it. Finally, the last thing that we talked about was end behavior. So when you're talking about end behavior, that always means that you're deciding what's happening for very, very large values of x and very, very big negative values of x. So for example, the first one that we did was x squared plus 4x minus 12. As this value gets bigger and bigger, or as this function gets bigger and bigger for x, it turns out that the same thing happens to the y value. So we write as x approaches infinity, y approaches infinity. And then we can also see that since it's squared, right, that as x approaches negative infinity, when you square a negative number, you're still going to get infinitely positive. Okay. Don't know what I just did. Oh, goodness. All right. Moving on. So for the next one, if you have 3x plus 5 over x plus 2, that was like our last one, right? Remember that with end behavior, we talked about how when you plug in super large values, it's only really the first term or the biggest term in the numerator and the denominator that matters. So you end up with 3x over x, which is really just 3. And that's going to tell you that for 3x plus 5 divided by the quantity x plus 2, as x approaches infinity, y approaches 3. And as x approaches negative infinity, y also approaches 3. Notice how the 3 does not depend on x at all. It's just telling us that as x gets really, really large, we simplify to 3, or something really close to 3. Notice this also tells us the horizontal asymptotes. So you can kind of think of end behavior in the same way as you think about those horizontal asymptotes. Let's look at another function. If we had x squared plus 1 divided by the quantity x cubed minus 5. So in this case, when we're looking at end behavior, remember we're just going to look at the largest term in both. That's what affects things the most at the ends of the days. So we end up with x squared over x cubed, which is really just 1 over x. So when you're looking at 1 over x, as x gets really, really large, you end up with a fraction, like 1 over a million, which ends up being really close to 0. So we can say as x approaches infinity, y approaches 0. The same thing will be true when you look at negative infinity. It'll be a negative number, but also still really close to 0. Finally, if you look at another function, this is the last kind of major type. If you look at x squared plus 3x plus 1 over x minus 5, we look at our biggest terms, x squared and x. So we have x squared over x as we get really large, which simplifies to x. Now, when we're looking at x, if you think about x approaching infinity, it's going to do the same thing, right? If the y values are approaching x, then as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y would also approach negative infinity. All right, so I think that's about where I wanted to be at for our review, or where we should be at so far. The next thing I'd like you guys to do is check out problems 67 and 68 from your textbook. So please do that, and then when you're ready to see how to do it, you can come back to this video.